Hello and welcome back. As we mentioned before, the channel has changed name from AAA Networking to FinetLink. I invite you to subscribe to this channel and hit the notification button so you will be notified for the new videos that will be uploaded. Help us grow. And after we saw the IPv4 addressing, now we will be focused at the IPv6 addressing. It is important to learn about the IPv6 addressing because in many networks you will find both IPv4 and IPv6 working together. After the hard work of learning to subnet an IPv4 network, you may find that subnetting an IPv6 network is much easier. And the objective of this module, that is divided in three parts, is to implement an IPv6 addressing scheme. The topics that we will include in this module will be the IPv4 issues, where we will explain the need for IPv6 addressing. We will see the IPv6 address representation, where we will explain how IPv6 addresses are represented. We will see the IPv6 address types, where we will compare types of IPv6 network addresses, and we will see and explain how to configure static global unicast and link local IPv6 network addresses. We will explain how to configure global unicast address dynamically, and we will configure link local address dynamically too. We will even identify the IPv6 addresses, and lastly but not least for the importance, we will implement a subnetted IPv6 addressing scheme, same as the IPv4 network. We have mentioned many times that IPv4 is running out of addresses, and this is one reason when we need to learn more about the IPv6. The IPv6 is designed to be the successor to the IPv4, and it has a larger 128-bit address space, which provides us 340 undecillion possible addresses. Since it is developed as a successor to the IPv4, it is used with this opportunity to fix the limitation of IPv4 and include enhancement. One example is the Internet Control Message Protocol version 6, which includes address resolution and address auto-configuration that is not found at the Internet Control Message Protocol version 4. The depletion of the IPv4 address space has been the motivating factor for moving to IPv6. As Africa, Asia, and other areas of the world become more connected to the Internet, there are not enough IPv4 addresses to accommodate this growth. The IPv4 has a theoretical maximum of 4.3 billion addresses. Private addresses in combination with network address translation has been instrumental in slowing the depletion of IPv4 address space. However, the network address translation is problematic for many applications by creating latency and has limitations that severely impede peer-to-peer communication. The Internet of today is significantly different than the Internet of past decades. The Internet of today is more than email, web pages, and file transfer between computers. The evolving Internet is becoming an Internet of things. No longer will the only device accessing the Internet be computer, tablets, and smartphones. The sensor-equipped Internet-ready devices of tomorrow will include everything from automobiles and biomedical devices to household application and natural ecosystem. With an increasing Internet population, a limited IPv4 address space using with network address translation and the Internet of Things, the time has become to beginning of the transition to the IPv6. IPv6 and IPv4 will coexist in the near future, and the transition will take several years. There are various protocols and tools to help network administrators migrate their network to the IPv6. The migration techniques can be divided into three main categories, and the dual stack will allow IPv4 and IPv6 to coexist on the same network segment. Dual stack devices run both IPv4 and IPv6 protocol stacks simultaneously. Known as a native IPv6, this means that the customer network has an IPv6 connection to their internet service provider and it is able to access content found on the internet over IPv6. The second one is tunneling, where it is a method of transporting an IPv6 packet over an IPv4 network, and the IPv6 packet is encapsulated inside the IPv4 packet, similar to other types of data. And the last one is the translation, where it uses the network address translation 64, which allows the IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to network address translation for the IPv4 networks. An IPv6 packet is translated to an IPv4 packet, and an IPv4 packet is translated to an IPv6 packet. Tunneling and translation are transition to native IPv6 and should only be used where needed. The goal should be native IPv6 communication from source to the destination. The first step to learning about IPv6 in network is to understand the way an IPv6 address is written and formatted. IPv6 addresses are much larger than IPv4 addresses, and this is why we are unlikely to run out of them. IPv6 addresses are 128 bits in length and written as a string of hexadecimal values. Every 4 bits is represented by a single hexadecimal digit for a total of 32 hexadecimal values, as it is shown here. It is not case sensitive and can be written in either lower or upper cases. Here it is shown the preferred format for writing an IPv6 addresses with X, which each X consists of 4 hexadecimal values, and the term octet refers to the 8 bits of an IPv4 address. In IPv6, an hexstat is the unofficial term used to refer to a segment of 16 bits or 4 hexadecimal values. Each X is a single hexstat which is 16 bits of 4 hexadecimal digits. The preferred format means that you write IPv6 address using all 32 hexadecimal digits. It does not necessarily mean that it is the ideal method for writing the IPv6 address. You will see the rules that help to reduce the number of digits needed to represent an IPv6 address. And here it is an example of IPv6 addresses in the preferred format. The first rule to help reduce the notation of IPv6 addresses is to omit any leading zeros in any hexstat. There are examples here listed how to do the omit leading zeros, and you have to know that this rule only applies to leading zeros, not to trailing zeros, because otherwise the address would be ambiguous, which means that we have to omit the zeros that do not have any value at the hexstat. By using this rule, here are listed some IPv6 addresses, how they are written, so the type and the format, and by no leading zeros, how it will be written. So as you can see, there are hexstats here, and the first hexstat can be written as it is, and here you can omit this 0 because it doesn't have any value, and it can be written in this form. And the third hexstat, you can omit the first 3 zeros, and then you can write in this way. And here at the last one, so you have to omit only the zeros that do not have any value at the hexstat. And this hexstat can be written in this way if we will use the first rule with no leading zeros. Let's get another example of this one. So this is the preferred IPv6 address, and here it is with no leading zeros. The first hexstat, the second one, you can omit all of the first three zeros in all these three hexstats, and here by omitting the zeros we have this number for this hexstat. If you are going to the last one, all hexstat has the value 0. In all of them you can omit the first three one and use only the last one to write the hexstat. And this is the format after we use the first rule. The second rule to help reduce the notation of IPv6 addresses is that a double colon can replace any single contiguous string of one or more 16 hexstats consisting on all zeros. So the double colon can only be used once within an address, otherwise there would be more than one possible resulting address. When used with omitting leading zero technique, the notation of IPv6 address can often be greatly reduced. This is commonly known as the compressed format. And there are some examples of addresses that has more than one contiguous string of all zero hexstats. And the best practice is to use the double colon on the longest string. If the strings are equal, the first string should be used the double colon. So if we are going to omit leading zeros and all zero segments, we will go from the preferred to the compressed. So by using the first root omitting zeros, we will go from the preferred IPv6 address to the compressed space address. And as you can see here, there are three contiguous hexstats that has their value as 0. So in this case, for both of we will use the double colon. So by using the double colon, we will go to the compressed IPv6 address as it is shown here. And if you see the second one, we have the preferred IPv6 address. And as you can see, only the first two hexstats has the different values. And the fifth one. And as you can see, here are the third and the fourth octet with 0 contiguous and the last three. And as we said that the best practice is to use the double colon on the longest string, so we will use the double colon here. And after we compress, we will be here. So the double colon will be for the last three of that. Let's see this one. We have this preferred IPv6 address. After we use the omitting leading 0, we will have this one, and after we compress by using the double colon, we will be here at the last line. Same will be here, and as you can see at the last one, all hexstat has the value of 0, and if we compress that, we will be at the only two columns. Same with IPv4 network, there are different types of IPv6 addresses. In fact, there are three broad categories of IPv6 address. We have the Unicast IPv6 address, which uniquely identifies an interface of an IPv6 enabled device. We have the Multicast IPv6 address, which is used to send a single IPv6 packet to multiple destinations. And we have even the Anycast address, which is any IPv6 unicast address that can be assigned to multiple devices. But a packet sent to an unicast address is routed to the nearest device that is having that address. The Anycast address are beyond the scope of this course, so we will be not focused on that. But remember this, unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all nodes multicast address that essentially gave us the same result. The prefix or network portion of an IPv4 address can be identified by a dotted decimal subnet mask or prefix length, which is shown with slash notation, and we have explained that at the IPv4 subnetting. In IPv6, it is only called the prefix length. IPv6 does not use the dotted decimal subnet mask notation. Like IPv4, the prefix length is represented in slash notation, and it is used to indicate the network portion of an IPv6 address. The prefix length can be ranged from 0 to 128. The recommended IPv6 prefix length for LANs and most other type of network is /64, as it is shown here. The prefix or network portion of the address is 64 bits in length, leaving another 64 bits for the interface ID or host portion of the address. It is strongly recommended to use a 64-bit interface ID for most of the networks. This is because the stateless address auto configuration uses 64 bits for the interface ID. It also makes subnetting easier to create and manage. An IPv6 unicast address uniquely identifies an interface of an IPv6 enabled device. A packet sent to unicast address is received by the interface which is assigned that address. Similar to IPv4, a source IPv6 address must be a unique address. The destination IPv6 address can be either a unicast or multicast address. Here in the figure, it is shown the different type of IPv6 unicast address. Unlike IPv4 devices that have only a single address, IPv6 addresses typically have two unicast addresses. It is the global unicast address, which we stand with the letters GUA. This is similar to a public IPv4 address. These are globally unique Internet routable addresses. The global unicast address can be configured statically or assigned dynamically. We have even the link local address. This is required for every IPv6 enabled device. The link local address are used to communicate with other devices on the same local link. With IPv6, the term link refers to a subnet. Link local addresses are configured to a single link. Their uniqueness must only be configured on that link because they are not routable beyond the link. In other words, routers will not forward packets with a link local source or destination address. The unique local addresses are not yet commonly implemented. Therefore, we only will cover the global unicast address and local link address configuration. The unique local addresses may eventually be used to address devices that should not be accessible from the outside, such as internal servers and printers. The IPv6 unique local addresses have some similarity with the private address for IPv4 network, but there are significant differences. The unique local address are used for local addressing within a site or between a limited number of sites. The unique local addresses can be used for devices that will never need to access another network, and they are not globally routed or translated to a global IPv6 address. The IPv6 global unicast addresses are globally unique and routable on the IPv6 internet. These addresses are equivalent to the public IPv4 addresses. Here in the figure, it is shown the range of values for the first hexadecimal, where the first hexadecimal digit for currently available global unicast addresses begins with a 2 or a 3, and this is only 1/8 of the total available IPv6 address space, excluding only a very small portion of other types of unicast and multicast addresses. And here it is shown the structure and range of the global unicast address. And as you can see here, we have the global routing prefix, which is the prefix or the network portion of the address that is assigned by the provider, such as an internet service provider, to a customer or a site. For example, it is common for the internet service provider to assign a /48 global routing prefix to its customer. The global routing prefix will usually vary depending on the policies of the internet service provider. We have even the subnet ID, which is the area between the global routing prefix and the interface ID. Unlike IPv4, where you must borrow bits from the host portion to create subnets, IPv6 was designed with subnetting in mind. The subnet ID is used by an organization to identify subnets within its site. The larger the subnet ID, the more subnets will be available. And we have even the interface ID, where it is equivalent to the host portion for an IPv4 address. The term interface ID is used because a single host may have multiple interfaces which having one or more IPv6 addresses. And here in the figure is shown an example of the structure of an IPv6 global unicast address. It is strongly recommended that in most cases /64 subnets should be used, which create a 64-bit interface ID. A 64-bit interface ID will allow us to have 18 quintillion devices or hosts per subnet. An IPv6 linked local address enables a device to communicate with other IPv6 enabled devices on the same link and only on that link, which means only on that subnet. Packets within a source or destination linked local address cannot be routed beyond the link from which the packet is originated. The global unicast address is not a requirement. However, every IPv6 enabled network interface must have a link local address. If a link local address is not configured manually on an interface, the device will automatically create its own without communicating with a DHCP server. IPv6 enabled hosts create an IPv6 link local address even if the device has not been assigned a global unicast IPv6 address. This allows the IPv6 enabled device to communicate with other IPv6 enabled devices on the same network. This includes communicating even with the default gateway, which means with the router. Here in the figure, it is shown an example of communicating using IPv6 link local address. As you can see, the PC is able to communicate directly with the printer using the local link address. And the next one, it is shown that some of the uses for the IPv6 link local address. You can see that the router uses the link local address of the neighbor router to send routing updates, and the host of the link local address are a local router as the default gateway. There are two ways that a device can obtain a link local address. One is statically, which means that the device has been manually configured by the administrator, and dynamically, this means that the device creates its own interface ID by using randomly generated values or using the extended unique identifier method, which uses the client MAC address along with additional bits. That was all about the first part of the IPv6 addressing, where we saw the IPv4 issues, the IPv6 address representation, and even the IPv6 address types. Thank you for being with me, and see you at the next session.